Okay, so we are wrapping up chapter 14, and they're starting out with they call it the Walsh diagram. It's kind of odd to be wrapping up a chapter on something that you don't even really care about because it refers to chapter 15. But it's pretty much just saying that you have all these molecular orbitals and how their energy changes, right? How their energy changes with orientation, right? With geometry in the molecule. And the only thing out of this that I really see is lines can't cross for molecular orbitals that have the same symmetry. Like pi and sigma, they have different symmetry, so they can cross. So, but it's nothing to worry about because we're not going to see it until we can talk about that stuff till next chapter.
Is this thing recording?
I thought so, wasn't it? Yep.
Cool.
So non-bonding, so it doesn't contribute to the bonding character, doesn't contribute to the anti-bonding character. That would be a molecular orbital that's pretty much where on the energy scale in comparison to the atomic orbitals that you made the molecular orbitals from. Be pretty much where.
I'm sorry, what was the question?
Right? Here's the atomic orbital energy level. This is energy. Here's atomic orbital energy levels that you made the molecular orbitals from. Bonding molecular orbitals in energy are where? Lower. Anti-bonding are higher. So non-bonding would probably be, yeah, pretty much right. Saying you're not helping anything, right? You're not helping anything. The Huckel approximation. So there's not a whole lot of information here either. This is, what I mean is our exams are so problem-based. So that's why there isn't a whole lot of helpful information here. But we've heard of the conjugated molecule, right? You have an alternating double and single bonds. But in molecular orbital theory, you don't know whose electrons are whose anyway, so everything really is delocalized. But that's kind of the organic talk. And then I think before they had Spartan, they said that all these overlap integrals, they were all zero. Every single one. They said they're all orthogonal, just because it makes the calculations so much easier. But that's not true. So Spartan doesn't do that, I'm sure. I think someone mentioned when you start having these, energy and all these molecular orbitals in here and all their energies, and you put them where they're at, you can have the lowest energy transition. And someone mentioned this already. From the HOMO to the LUMO. What are the supposed to be abbreviating? Highest occupied molecular orbital to the lowest unoccupied molecular orbital. Right? That's your frontier orbitals, your lowest energy transition. And these pi electrons and how they're lowering the energy and making things even more stable to describe what nature kind of developed here. The pi electron binding energy all involves the pi energy. Delocalization energy, we kind of mentioned it already, how if you alternating double and single bonds, you can actually lower the energy even more. But this whole section here is really referring to calculations in my view, right? And they have, like Spartan, semi-empirical methods. So if you want to, your goal is vibrational frequencies, or your goal in some chemical problem is geometry, or it's geometry, or what else are we interested in? Polarity, right? Where is the molecule polar, or where is regions of electronegativity, okay, or regions of somewhat positive charge. And those calculations can get really important because I remember, I can't draw DNA, but it's just like a helix, right? And and we were interested in these intercalating compounds, and we were modifying the compounds so that they would, intercalate better. Well, a lot of that is just van der Waals attraction in here with, high regions of electronegativity, high regions of polar. If it's really kind of electronegative, it's going to suck up where it's more positive. And what we're interested in is not only how the DNA is its chemical environment, but our compound itself. So we were really interested in polarity in a lot of those calculations. And they get really involved. And if you don't want to be sitting there forever waiting for your calculations to finish, you do semi-empirical methods. And all that is it uses fudge factors. It uses experimental data to make these predictions of whatever you're after, frequency, geometry, whatever. Okay. And those fudge factors are very often like ionization energies and that sort of thing. But whatever is known in the lab, they can incorporate into these calculations. But there's assumptions there when you start using those things. So it's a safer bet to do ab initio. That means there's no fudge factors whatsoever. Everything is complete theory. All theory, no fudge factors. Okay. And here, if you have I don't know if you remember doing Spartan, but you had all these different options to do the calculations and all these different dialog boxes you could pick. Here's another one, CNDO, complete neglect of differential overlap. If you have different orbitals on different nuclei, all right, their overlap integral was 0. So they're really, like I said, this section, I'm just trying to get to the problems because this section isn't too involved. We have Gaussian type orbitals. Really nice because, in the Schrödinger equation, you want to get your wave function back again. So Gaussian type orbitals work pretty well. So you see that a lot. And that's why they're mentioning that. Okay. Here I think I would weigh this section a little bit heavier. Okay. Band theory of solids. So pick a solid, I don't care. Silicon, sodium, iron, copper, right? What they're trying to say is they're trying to, I think you've had this in inorganic, right? Talked about band theory?
Very little, yeah.
Okay, so the idea here, I like how they kind of did it, except it'd be nice if they flipped it around. But here they took just one atom. Here they took 2 atoms. Here they took 3 atoms of this metal or this compound, whatever, pick one. And it's donating an atomic orbital, a 1s, a 2s, a 4p, whatever. They're donating an atomic orbital, 5s, 6s. Each atom is donating the same atomic orbital. And you're generating molecular orbitals. So if you have 1 atom, you have 1 molecular orbital. If you have 2 atoms, you generate 2 molecular orbitals, and on down. Okay, so you just keep going and going and going. But a solid has a lot more than 6 atoms, has, right, gazillions of them. So what you end up with is a band of all these molecular orbitals. And at the bottom, right, let's go back here. Before, our molecular orbital energy diagrams look like, where is it? Oh, that was the last. No, here they are. Here's what our molecular orbital energy diagrams look like for molecules. But for metals, man, everything is just, there's so many. I mean, that's a molecule. We're not talking about molecules. We're talking about a solid. So many more molecular orbitals. Whoop, where did it go? Right? That you end up having a band. And at the bottom of this band, you can't even tell the energy difference between these guys. They're so close in energy. At the bottom are your bonding molecular orbitals. At the top are your anti-bonding molecular orbitals. And I guess right in the very middle would be called non-bonding. Okay? But so that's how this is looking. So okay. And then yep.
Like the one that for the
Yeah.
What would the antibonding at the top?
I don't think there's enough to even have a. There's not enough to have a band. So you only have 3 atoms. So all they're trying to show is they're trying to show how. Well, I guess with 3, maybe you have a. Maybe in their diagram they're trying to say that you have an anti, a non, and a bonding with 3, just one of each. But for me, it doesn't even really make sense because a solid doesn't have 3 atoms. That sounds more like a molecule to me. So, and I guess that kind of makes sense if you think of it more as a molecule, because it looks more like it resembles more this kind of thing. But we don't have solids of 3 atoms. We have solids of many, 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 right? So this is what we end up with. But I think this is what they're trying to show, Ashley. I think you brought it out. They're trying to show that if you have 3 atoms, you get 3 atomic orbitals, you end up with 3 molecular orbitals, an anti-bonding, a non-bonding, and a bonding. All right, with 4, looks like you end up with 2 of each. And then it just keeps going on from there. So a metallic conductor, just flip over to here, the band would look like this. All right, where that band that's of molecular orbitals that's generated is just not filled up. Filled up with what?
Yeah, that's what I'm saying.
Filled up with what? What are we filling these molecular orbitals up with? What goes in orbitals? Electrons, right? So if you have however many atoms however many electrons were, however many orbitals are being generated, that's how many electrons were being generated. And if the band ended up looking like this, it's just not filled up, oh man, it's going to conduct. Look at all these unoccupied energy levels. And it'll conduct so easily, right? Usually we think of, electrons have to get promoted. Well, my goodness, it's a continuous band. There's nothing really to promote. So the energy difference is so low between the LUMO and the HOMO, right? So the top energy level of filled electrons is called the Fermi level. Okay, that's what they call the Fermi level. But not everything is a metallic conductor, right? Now I'll back up and finish the story here. If you have a metallic conductor, what happens to the resistance as you increase the temperature? So you have a metal, you have a conductor. This is how we're supposed to be thinking about how it conducts electricity. If you increase the temperature
Increases the conductivity. It decreases the
with resistivity, it decreases the conductivity. It increases the resistance, right? And I don't know, conceptually, you just think of more things being in the way, I guess, somehow,
Oh, really?
right? That things are just, right? But I mean, it's not that big of a deal. It's not like, oh, it's not going to work anymore. Oh, come on. Computers, everything works when they're warm. The point is just that resistivity increases a little bit, right? Okay. So all we're talking about solids. So all we're talking about is that if you have a metal, increase the temperature, the resistivity increases a little bit. It doesn't function as well.
That's if you have a metal, right?
That's if you have a metal.
Oh, okay.
Well, if resistivity increases, I would say conductivity decreases, right? I would say that's how that would have to work. But not everything's a metal. We have semiconductors. Okay. So with semiconductors, now we don't have an individual band anymore. To explain a semiconductor, we have to have 2 bands, right? This might be an illustration of a semiconductor, where we have an S band and a P band. They call it S band because each metallic or semiconductor atom donated an s orbital. Here, to generate a P band, each atom donated a p atomic orbital. So you get a P band and S band. But the point is that there's some energy difference between the two, and a band gap. Okay.
Was one also called the valence band or something like that?
No, I don't think they use that. Well, hold it. Maybe they do. I bet you're right.
Something like that in the energy.
Look at that. If you blow this up,
You call one
if you blow this up,
there you go.
Yeah. So when you're talking about, yeah, I guess they do. When you're talking about semiconductors, right, your lower band, right, is pretty much filled up. So if it's filled up, there's no molecular orbitals readily available to conduct electricity. Okay. So they got to jump. They got to jump the band gap. Okay. Well, that takes energy. So with a semiconductor, what happens to resistivity? If it's really cold, your resistivity should be pretty dang high, I would think, right? But as you warm it up, the resistivity should go.
That's the one that goes, connectivity increases, resistivity decreases.
Yeah, it'll conduct at higher energy, at higher temperatures. Resistivity goes down because those electrons get promoted into the conduction band. Okay. Now, but you don't, why just have temperature control things? That's pretty primitive. Why not replace, because these are crystals, why not replace some of these atoms with something that doesn't have as many electrons, right? Dope it, right? You can dope it with something that doesn't donate as many electrons as the atoms around it. Then you're going to have some holes. They call them holes in here. Or donate it with something that has more electrons than those atoms around it. Then you're going to be filling up that a little bit. And this is all at just room temp. So you can control the conductivity of these compounds. So then you're getting into semiconductors. And that's what this is kind of talking about. Where is that? Dopants. Right? And create some positive holes or N-type dopants. Something just have atoms in there, replace silicon atoms with, right? Where's silicon? Arsenic atoms, right? Arsenic has more electrons than silicon. So you can and they've done a lot of research on that. So what I'd like to do is knock out these questions right here. Yep.
So if you dope something that has less electrons, it creates holes?
Yeah, because less electrons, you're not going to be filling up the valence band. It's not going to be full.
Okay.
Right? Now it's going to be, because you replace some of those silicon atoms with something that doesn't donate as many electrons. So it'll look like this. Right? It won't be full. Your Fermi level will be lowered. I guess that would be the best way to say it. The Fermi level would be lowered. Now it can conduct. And the more you lower it, the better it will conduct. Or you could dope it with something that has additional electrons. Now you're raising the Fermi level. You're raising the Fermi level into the conduction band. So that's what dopants do. Oh, we didn't mention insulator. So we had metal. We had semiconductor. What would this? How would you explain this one?
I remember that one. It was the band gap that was like really large.
Yeah, it's gonna look just like this, except really just spread it out. Band gap is huge. They can't make the leap. Glass. Okay. Exercise 5. Let's take a look at these, and then we can take a look at the homework that was assigned for today. Give the parities of the 6 pi molecular orbitals of benzene, and we're supposed to use figure 14.44 as a hint. So if you find figure 14.44, yeah. Okay. So they said that there's 6 molecular orbitals of benzene. So on page 416, there they are. I should have scanned it and put it in there. But the point is totally don't look at the name, how they named them. It gets really confusing. Don't look at the name. First, what is parity? What was parity? Do you remember? If you go back to our molecular orbital diagram. Sometimes we have G's and U's, right? Sometimes you have G's or U's. What were that? That was Gerada and Ungerada or Ungerada. Okay. Well, these, I don't know, it's just extra information. They really didn't need to have them. But chapter 15 is really going to bring this out. It's all about symmetry and getting shortcuts and chemical calculations with symmetry. But you have to have a what to put these little subscripts on the molecular orbitals. You have to have a center of inversion. Does benzene have a center of inversion? It does, right? Most definitely. You can reflect through the center and get the same thing again. So its molecular orbitals should have parity, Gerada or Ungerada. So what you do is you go to page 416, disregard their naming of them, and just look at them and draw a line through. For example, start at the bottom, right? Now, what did the light and dark mean again? What did the light and dark regions mean? It meant that the what changed sign? The wave function. The wave function changed sign. So you just pick one. Wherever it's light, the wave function's positive. Wherever it's negative, well, wave function's negative. Wherever it's dark, it's negative. It really doesn't matter. The wave function changes sign. So if you reflect through the center of inversion on the bottom one, do you get the same thing every time? Yeah, you most definitely do. So on the bottom one, you would say that is Gerada. So you'd say A2U is Gerada. The next one up, right? Looks like we have two of them. But they're both what? Parity. If you reflect through the center, now they're not interested in seeing the same thing. They're interested in this wave function sign.
Ungerada, then.
It's Ungerada because you went from light to dark.
Yeah, positive.
So E1Gs are Ungerada. How about E2U? Reflect through the center.
Does it have to be a horizontal mirror?
Has to reflect through the center of inversion. You're reflecting through the center of inversion. That's the whole idea of center of inversion.
And Ungerada?
Ungerada. Because are they changing sign? They're not changing sign. You always go dark to dark or light to light, don't you?
Wait, I thought the last one we went from dark to light.
Yeah.
And this one's going from light to dark on the left and dark to light.
No. Reflect through the center. Where's the center?
Oh, I thought it was right here.
Well, that's not the center.
Oh, right here.
Where's the center of of the molecular orbital? There's the
Right
center.
there.
Here's the center. Here's the center. Reflect through the center. It goes from what color to what color?
Look diagonal.
Reflect through the center.
It's center
Okay.
inversion.
Center of inversion. So yeah, you have to put a dot at the center of inversion. And that's always the very center of the molecule, right?
Yeah.
So it goes from what to what every single time.
Okay. Positive to positive, negative to negative.
Yeah. So this
Okay.
would be
Gerada.
Gerada.
Not Ungerada.
Gerada. And the last one, so ETU. And the last one would be
Is that one also Gerada?
very top one. Put a dot in the center and reflect through it. Did the wave function change sign? Yeah, it goes from dark to light every single, no matter how you do it, it goes from dark to light. So that'd be Un. B2G. What's the next one? Predict the electron configurations of a benzene anion, benzene cation. Estimate the pi bond energy in each case. I'm sure they gave us another hint. Yeah, they want us to use figure 14.44 again.
Okay.
All right, that's what the hint says. What I'm trying to think here is what do they... How many electrons are we working with? First, we need to... What goes through my mind is they want the electron configuration. So that means we need something like this, right? Something that tells you, okay, well, we're going to fill 1 sigma g. You just follow this format, right? Go from top to bottom. That's one thing we need. Well, they gave that to us. They said use figure 14.44. That was your hint. So there they are. You're going to fill A2U first, right? And then you're going to fill E1G. Then you're going to fill, right? And notice, too, how A2U, the very bottom, for benzene on page 416, how many molecular orbitals are there?
For which one? A2U?
A2U. How many molecular orbitals are there?
1,
There's just one. So that means how many electrons can fit in that orbital?
2.
2. Okay, then you go up to the next molecular orbital, the next higher energy. That's E1G. Well, how many molecular orbitals do they have there? 2 of them. So now you have to fill it with 4. Okay, so they kind of already did benzene for you, right? They already said, if you take a look at the figure, they already did benzene for you. They said, hold on here, where am I? A2U2, E1G4, right? That would be, they already did that for you. That's benzene. Because they didn't say draw it out. They just said give the electron configuration. So there's benzene.
Which one would be the anion? Which one would be the
Okay, now they want the electron configuration of the benzene anion. Benzene anion. Well, that means what? If you have an anion. How many more electrons?
2.
Well, don't make your life more complicated than it needs to be. What's the simplest answer?
You want the most electrons.
No, to generate an anion, you're right. To create an anion, you have to donate electrons here. It has to accept some electrons. What's the easiest answer? How many electrons would you donate? 1, right? So what would be your new electron configuration then? A2U2, keep going.
E1G3.
E1G, whoa. You donated an electron, didn't you? You just took one away. If you say E1G3, that's not the anion, that would be the... Okay, fine, we can do that one first.
So then the anion would E1G4. Or E4 1D.
So now then you want the anion.
E5.
So you'd say anion would be...
A2, E2U. E then E5.
Okay. Now what's wrong with this? Look at the diagram. It can only hold 4. So this guy, you better stop at what number? Not 5, 4.
So then go to E2.
What's the next one? You don't have to memorize, just look at the diagram.
Okay, E2U.
E2U,
E then
1.
1. Okay.
Okay. Then if you, then they want to estimate the pi bond energy in each case. So this is from the reading. You got to dig this out of the reading. And because it says right here in the very middle, if you're on page 416. On page 416, it's just talking about benzene. And its diagram, benzene has how many valence electrons in there?
Altogether?
Yeah, there's 6, right? Okay, so if you look at the very middle of that page where it says the pi electron energy of benzene is? Okay, So look, it has 2 times alpha plus 2 beta plus 4 times alpha plus beta. So where's the 2 and the 4 coming from?
The electron.
The electrons, yeah. So that alpha plus 2 beta has to correspond with the energy of the A2U, right? And the alpha plus beta has to correspond to the energy of the which molecular orbital? Because there's 4 of them.
What would be different for alpha plus beta?
Well, no. They're saying alpha plus 2 beta, 2 of them. So this, you want the energy. So you have to add up the energy for the A2U orbital twice. You have to add up the energy for the E1G orbital, not twice, but 4 times. So that's why they have 4, because you have 4 electrons. So they have 4 times alpha plus beta, 2 times alpha plus 2 beta. So where are they getting this alpha and beta stuff? That's just in the reading. They say that's your energy. That's your energy for these orbitals. So A2U, they said that's alpha plus 2 beta. E1G, that's just alpha plus beta. E2U, if you look in the reading, that's alpha minus beta. So that's pretty much all we're going to do. All right, for the cation, that energy would be 2 times its energy for that orbital plus 3 times its energy for its orbital. The anion, again, 2 times its energy plus 4 times its energy plus 1 times its energy. Okay. And where do you get these energies, like 2 times, well, the A2U, and get it from the reading. And they said it was alpha plus 2 beta. Thanks. Alpha plus 2 beta. And then the E1G we said was just alpha plus beta. So we can catch all these up here. Okay, so this has to be alpha plus 2 beta. This has to be alpha plus beta. And the E...
Alpha minus beta, right?
Oh, thank you, alpha minus beta. Okay. And then I think if you want to get the answers in the back of the book, you just have to simplify this. Combine the alphas and combine the betas, and then you get, like here you get 2 alpha and 3 alpha. That'd be 5 alpha plus 4, 7 beta. All right, if you want to get the answers in the back of the book. Okay. So that's all they're trying to do.
Okay.
I see the alpha plus 2 beta and the alpha plus beta, but where's the
Where?
alpha minus?
I got it out of the reading somewhere. Where did I get it? Let's see.
Would it be 46?
Would it be what?
There's like, it says like alpha plus beta, alpha minus beta.
Yeah.
Plus or minus beta.
I dug it out of the reading somewhere. I could have just assumed it. Because the plus combinations are almost always the bonding, and the minus are the anti-bonding. That's probably what I did. All right, that it said the roots are alpha plus beta and alpha minus beta. So, and you can see that here, if these are your molecular orbitals, this has to be bonding because benzene exists. So this has to be bonding molecular orbitals. These must be anti-bonding molecular orbitals. So the minus combination, I just put it on this one. And it gives the right answers in the back of the book. Or I found it in the reading somewhere. I don't see it now. Okay. So the homework for today, did you have any questions on that? Because we're not going to turn it in because you need it for the exam.
What the homework due today?
Yeah, we're not going to turn it in because we have an exam on Monday.
Then we want
No way I'll get it back to you. We don't have class on Friday. We have that stinking. We have that OLU symposium. Yeah, so sorry. I'm glad you asked. I didn't even tell you guys. Class on Friday. So there's no class on Friday. We have lab tomorrow though. We have lab tomorrow because that symposium thing doesn't start until noon or whatever. In that symposium thing, I have stickers. So I'll meet you over there and I'll give you your own special set of stickers. And first come, first serve, because I've got all these different kinds.
Are we going to be supplied the duct tags again?
I'll bring all that stuff, because who knows what they're going to have. I don't even know if they're going to have a bolt